So this warm-up is one of small tricks which you use to make things easier. I also read about another trick, but I'm not sure it works actually. What I read was by Hemingway, who wrote that when he writes his stories, he always stops at the moment in the evening, at the moment when he knows very well how to continue. He could continue, but he forces himself to stop. And then next morning he begins afresh. I tried this with mixed results, let's say. Okay, so we discussed last time the notion of symmetry. And it was the notion which we applied in many areas. Geometrically, it is a transformation which, say, moves the certain geometrical configuration into itself. That was one of the definitions. When we talked about the equations, the symmetry meant that we know the prescription, how to generate all solution from the new solution, from the old solutions. So we discussed plenty of various symmetries, time reversal, time translation, space rotation, and so on. And basically what we meant was that, say, in the case of time reversal, we said that if we have a particular solution for a dynamical system, a particular solution of the Newton equation, we said that we can form a new solution by changing the argument, and x tilde will satisfy the same Newton equation as does x, and but it's important. Or you can do any other transformation. What is important is to realize that symmetry doesn't mean that the solution goes into the solution, into itself. Generally speaking, that's not. It can. There are some trajectories for which x of t is the even function. But generally speaking, the symmetry, it's too strong to require. The symmetry just means that you generate new solution from the old one. And I actually forgot to tell you one purely mathematical example of this, which will help you with the homework a little bit. So let's consider a very simple, the simplest imaginable equation. X dot of t is equal to x of t. I will show you in a minute that symmetries are so powerful that they define the solution. So what are the symmetries of these equations? There are, it's not one, there are a couple of symmetries which I want you to tell me about. Something, I'm not talking about something fancy, it's very straightforward.
Spatial reflection?
Reflection, you suggest, yes, it is a symmetry. Indeed, if we define x, sometimes I will be using this notation, sometimes the meaning that x tilde of t is minus x of t. That's a possibility. Although I am more interested at the moment in continuous symmetries. This is a discrete symmetry. By the way, talking about discrete, is there a time reversal symmetry here? No, right. Okay, so what is the what are other possibilities? are the very simple, straightforward possibilities. We can discuss symmetry when we transform X, and we can discuss symmetry when we transform the argument. What can we do with the argument? Go ahead, please.
Now with the argument, I was going to say scale X.
Yes, very good. We will need this. Of course, this is a new solution of this equation, and I need one more symmetry. And then we will see how the symmetry determines. Yeah, go ahead.
We can add a constant to the time.
Yes, time translation symmetry. Time translation symmetry. And now we have a puzzle because the puzzle is that generally when you have first order differential equation, its solution depends on, there are infinite number of solutions, of course, and this solution depends on arbitrary constants. How many, in the case of this equation, how many arbitrary constants are contained in the solution? So what have you? I can put. I can ask the question more physically. What kind of data you should fix to fix a solution in this equation? What do you? Yeah, go ahead.
Initial time and location.
Okay. So generally, if we take some particular moment of time, you can fix, in this case, x of 0. And that's general for, you cannot fix time and velocity, by the way, because velocity will be determined from the equation. It's not arbitrary. However, this initial position is arbitrary, and so indeed if you call it C, you get a general solution which depends on this constant C. And that's completely general. If you have any function of x here, but first derivative here, you always have a solution which depends on one arbitrary constant. But now it seems to clash with the fact that we can generate solution which depends on two arbitrary constants, namely lambda here is arbitrary and a here is arbitrary. So contrary to the general theorem, which tells you that there is only one arbitrary constant in the solution, that solutions are parametrized by one arbitrary constant for the first order. By the way, for the second order, what would be the, would I put x double dot here, then what? Then how many constants I will have? What can I fix? I'm digressing, but just it's important for us to understand this clearly. Suppose you have some Newton equation like that. How many general, how many how many constants contained in, what can you fix here in an arbitrary way?
So the initial position in first derivative.
That's correct. You see, here I couldn't fix first derivative because the equation tells me what it is. It doesn't allow, the equation doesn't allow me to fix x dot at 0 in an arbitrary way. Here, x dot doesn't enter. So the equation allows me to fix x and x dot. We will return to this later, but I now want to finish the so the general solution of the second order differential equation, it contains two arbitrary constants. in order to fix the motion, in order to select a unique trajectory in the Newton case, it's not enough to fix the initial position, you have to fix the initial velocity also. So, but returning to our toy model, here it's only one constant, but using symmetry we generated the solutions which seems to have two arbitrary constants. We can always write down write it down in this way. So, on the other hand, we know that it should be only one arbitrary constant. So, what kind of conclusion we should make from this? You are allowed to secretly consider the explicit form of the solution of this equation to answer this question, or you can figure it out. So what I'm driving at is that this clash between two symmetries and the fact that we know that there is only one constant leads you to a certain relation, to a certain functional equation. So what you it actually means that will be in the homework. It actually means there is only one way out from this. That when you take x of t plus a, you get a new solution. But you can, when you multiply it by lambda, you can always choose lambda in such a way that this is a null solution. And from this, it all, of course, we now can see it in a very simple way. You just say x of t is some constant e to the t. This is a solution. And if we take x of t plus a, we get c e to the a e to the t. If we get lambda x of t, we have lambda c e to the t. And so you see that, in fact, in this case, it's completely trivial, but it will be less trivial in the exercises, less trivial examples, although still. But it shows you that indeed we must have, and we do have this functional equation. I will not go into this now. This equation actually can be viewed as a definition of the exponent. And there will be, my goal here is not to analyze this equation, but to show you the way, a method of thinking about much more, this equation, is trivial, completely trivial. But you can use this logic in complicated cases, and we will. So, and in the exercises, we will give you similar equations, slightly more complicated, nonlinear, and so on. And once again, the symmetry there will allow to find the solution. Okay, we also didn't want to go to too many details here. We also looked at the completely different application of symmetries. Namely, we looked at some reactions between elementary particles. We said that these reactions, quantum theory and experiment determines the probability of various reactions which depend on momenta. and maybe on some other variables like spin electrons, like particle spins and so on. What rotational symmetry tells us is that these probabilities, well, what it tells us is basically that you can rotate the apparatus provided there is no gravity. It would be a little difficult to rotate the LHC, but in principle, if you rotate the apparatus, then probability of various reactions will be unchanged. And from that we derived that it is the function of various scalar products and pi square. And we saw that in beta decay, what appears is that the probability has the following structure. And we said that that means that if you have only two vectors, then you cannot decide whether reflection symmetry was broken or not, because if rotational symmetry is preserved, the expression will be automatically symmetric under reflection if it depends on two vectors only. But with three vectors, it's not. It's like that. By the way, and A and B are functions, of course, of scalar products. By the way, a question before we leave this. I'm writing only first power of this triple product. Why is that? Why I don't care about, well, you could have second power, third power, and so on, it seems. However, it's irrelevant. Can you figure out why? Why it is completely general to write the probability, rotational invariant probability, in this form, where A and B are rotational function, without adding higher powers of the triple product? It's again a curious fact about symmetry. Let's suppose I will take the second power of this triple product. Will it be breaking mirror symmetry or not? No. What conclusion can you make from the fact that the square of this expression doesn't break mirror symmetry?
I think it can be expressed as a function of pi of pj.
Absolutely, absolutely. That's the point. That when you take the second power, it's a function of the ordinary scalar product, and that's because of the symmetry. That's because when you take the second power, it's reflection symmetric, and reflection symmetric means that it depends on scalar product. And of course, you know the well-known formula of vector analysis, which tell you so. And therefore, if you take the third power, it's the same as writing the first power, because it's just modify functions A and B. So very schematically, that's how you determine experimentally breakdown of in quantum theory it's called parity, this reflection symmetry. Okay.
Could you re-clarify how pi, pj, and pi squared are the only possibilities given rotational symmetry?
Yeah. So the question is how to prove it, or it is
how we know there's nothing else.
Yeah. Well, right. We know this you can prove this by looking at this condition. I will not go into the full proof, but the idea is very simple. You write down you consider infinitesimal rotations. Infinitesimal rotations, maybe I will use them a little later. It's a scalar product of the angle of rotation multiplied by this. And so you get the condition that W of pi plus delta pi is the same as W of pi. Delta pi is infinitesimal variation of these guys. And so I get the equation that sum pi d pi W is equal to 0. And and then you prove you can solve this equation and prove that this is the only solution. So that's generally the approach. There are quite a few details to be filled there. I can tell you if you are interested after the class how to go ahead with it. But what's worth understanding is the general method. The general method is that you look at the invariance condition. You say that let's assume that the certain function is unchanged when you change variables in a certain way. And that gives you the partial differential equation like that. And then you have to go, you have to proceed. But that was a quite legitimate question because I based my statement on the fact that I assume that this is proved. It's obvious that this is invariant under rotation, but it's not obvious that this is the only invariant thing. Okay, so so far we discussed symmetry in a rather kinematic and superficial way. And now we will improve it a little bit. In dynamics, symmetries have much deeper significance than just simple facts like that. And they have much deeper significance because for some reasons classical dynamics contains the new principles called the least action principle or variational principles, which make symmetry much more powerful tool than simply kinematical analysis, which we did. So we will discuss, to some extent, I'm sure you encountered with the least action principles. There are a couple of very good exposition of these principles. The book by Landau and Lifshitz begins with discussion of the least action principle in a very brilliant way. It was actually the thing this book made, this discussion made a great impression on me when I was in high school. A fantastic book. And the second very good discussion you'll find in Feynman's lectures. There are also good mathematical books by Gelfand on variational calculus, which we'll need. Of course, I will not follow these books. I will try to do something complementary to these books. As for the choice of the books, there is, I would say, a general principle which I usually follow. Just read the books written by great scientists. Because if it is written by mediocre scientists, how can he teach you to do great work? He doesn't know how to do it. There are exceptions of these rules. Some books written by greatest scientists are impossible to read. In any case, as years pass by, I become less categorical about that. So, but as a rule of thumb, it still works. What the variational principle tells you is that you can determine the motion of the system not by solving the Newton equation, but by minimizing a certain expression called action. The origin of this idea came from optics. In optics, imagine that we have a light source and it's what I'm describing is the Fermat principle. This is a mirror, and the time which light takes to go from A to B should be minimal. So let's look at another option. Suppose this is the middle of this, and suppose that we in fact try to propagate light along the trajectory displaced from the middle, from the symmetrical point. And then we will find, after some trigonometric exercise, we will find some time, which is, we assume that this is vacuum, so time is proportional to the length of the trajectory. It will depend on L. And the T of L, of course, you can calculate. It's some trigonometric expression, but I intentionally don't want to do this. And instead, I want to ask you for the argument how T of L depends on L. How to argue from just this picture and just this unwritten expression, how to argue that the minimal path, the minimal length, minimal time to go will be if we are going through the middle here. So this is precisely the middle of this link, and you can compare. It's not entirely obvious that, although it's pretty obvious that this trajectory is shorter. How? But you don't. Yeah, go ahead.
If you take any L, you can trace an ellipse with it.
Yes.
And then you'll see that it goes further down when it comes to
That's correct. That's one of the possibilities, but that's not what I want. Your answer is completely right. But you see, sometimes you need not simply the right statements, but the statements which are formulated in a certain way, because there are many ways, to solve the problem. But some methods allow you to generalize easily. Other methods don't. And so I'm now looking for the methods which will be generalizable. And for that, I would like to ask you, what is T of minus L? Suppose I will take.
T of L.
Yeah, okay. So T of L, it's obvious, it's again symmetry with respect to reflection. T of minus L. Okay. now you have it all. Last logical step will tell you that T of L is extremal, is an extremum. How would you argue that that T of L has a minimum or maximum when you are here?
dTdL equals negative dt negative L.
That's right. Or you can simply, that's correct answer. You can simply write down for small l an expansion T of 0 plus T prime 0 L plus T 1/2 T double prime 0 L square plus etc. And now you conclude immediately that because it must be an even function of L, T prime at 0 is 0. But that's precisely the condition for the extremum. So you see, you don't have to calculate anything. You just have to figure out on the basis of symmetry that this is a... Okay, now let's generalize it a little bit. If we have if we have some refraction index, the speed of light is equal to 1. Speed of light in the vacuum is 1, and we have the formula like that. I'm sorry. So we have the expression if we have a trajectory x of s, we have an expression integral dx. Well, I should probably do it a slightly different way. We start with next example when we have two media, and so this is Fermat, this is Snell's law, it's called, which tells you that if we have and once again, it's very easy to find this that this minimizes the time needed for the light to go. And you can generalize it a little bit, as I intended. You can consider a medium where the refraction index depends on x. And the time which is the integral over the path over dx divided by the speed of light c of x, and speed of light is getting this. Speed of light is the same as the refraction index. So we have to learn, that's what we will be doing, we have to learn how to extremize such expression. We see by these examples that condition of the extremum can actually determine the trajectory. And you can understand it qualitatively. It's like if you have different n so that the light propagates very slowly in some region, you want to avoid this region. Although it becomes longer, the path becomes longer, but you avoid the region with slow light. And what is quite amazing is that, first of all, this is well-defined mathematical problem, which gives rise to the whole part of mathematics, the variational calculus, and I will explain the basics of this. And even more surprising is that mechanical system satisfy the same principle. That you can determine the trajectory from the condition that certain expression is extremal. And in many cases, it's minimal. It's a minimum. Well, that may. Moreover, from this we will see, maybe today, maybe next lecture, that there is a close analogy between the motion, mechanical motion of a particle in a potential, and propagation of light with a certain refraction index. The potential will be expressed in terms of the refraction index. So there is this optical mechanical analogy coming from this variational principle. And also the symmetries in the case of this system becomes extremely meaningful. They mean that there are certain quantities which are conserved corresponding to each symmetry. So there are many, many things. I'm just telling it quickly because we will work out everything and we will see how powerful these variational principles are. By the way, then they were gradually discovered. At first there was Fermat principle, then people started thinking. Leibniz thought that mechanical system could be also discussed in these terms. Then there was a guy, Maupertuis, who formulated the variational principle for mechanics, which led to a lot of controversy because he was well, you see, the idea behind the variational principle was, of course, theological, that everything is done in the best possible way. And it was the age of enlightenment, and Voltaire was very unhappy about it and wrote a very satirical article about Maupertuis. And as a result, well, there was a lot of trouble for Voltaire because of this, because Friedrich the Great supported Maupertuis and so on. It was a complicated and interesting story. Voltaire was completely wrong, of course, but on the other hand, he wrote a very nice satirical piece, Candide, in which he laughed at the statement that everything is done in the best possible way. That's what I would say that his pamphlet against Maupertuis, I read it, it's pretty dull, but Candide is fine. It's kind of interesting. All right. So let us try to find, first by trials and errors, some discrete mechanical variational principle. First, we would like to see, well, let me first write down the answer, and then we will try to, people came to this answer by trials and errors. And the answer is that if you consider the trajectory. Consider a trajectory. It's some function of t. Kinetic energy is x dot square, and for the reason which will become later, we can look at the following quantity called action, which is integral over dt from t1 to t2. And you take the difference between, I'm talking about a single particle, the difference between the kinetic and potential energy. It's the reason why this minus appears here will be clear. Basically, what we will see is that if you put minus here, then the conserved quantity will contain a plus. It will be energy. But I'm running ahead of myself a little bit. So this part is very standard, but I shall use it. I have to go, and because of that, I will go very quickly. How we determine the trajectory which minimizes or extremizes this action. We basically follow the same principle how we extremize and minimize the function. Suppose you have a function of n variable. What is the condition for the extremum of this function? Forget about this thing, just an ordinary function of what is the, you want to find the minimum, suppose, of this function. What is this? Yeah, go ahead, please.
The derivative has to be 0.
The what?
The derivative has to be 0, and it has to be some lower value than the 2 negative.
Yeah, well, we'll say just that, right. We say that if we argue in the following way. First of all, we define what we mean by partial derivatives. Suppose we consider the case that all these variables are small. Or suppose they're they're not small, but we looked at some particular point, and we write down xk as xk star, this fixed point, plus a small variation of xk. I gradually introduce to you convenient notations for the future discussion. So we have the function and we can now expand it in terms of delta x. Delta x are just a notation. You call it. It's just a conventional notation, but you just can call it any other letter, say y or whatever. It's just some displacement of the original variables. So we'll write it down in this way, plus there will be linear term. I shall call it this function, this say ci of delta xi, plus there will be terms of the order of delta x square and higher orders, of course. Now we simply call what we call partial derivatives is those CI. CIs are nothing but partials. It's a definition of partial, if you wish, of partial derivative. You expand a function near some point, and you call the coefficient in front of the linear term. This term is linear in delta x, and the coefficient in front is, by definition, the partial derivative. And you calculate it in precisely this way, by expansion. And now, what is in these terms, what is the condition for the minimum or a maximum or extremum in general? Just to be, it's basically, you said it already, but I just want to repeat it to set up the language. So when the function f, when x star is an extremum point, we have this particular function, so it's a rather trivial question. So it's not some, yeah. Yeah, why is that?
Because otherwise you move in a certain direction.
That's right. You see, if this term is non-zero, it can be either positive or negative. So the only way, so if the function has a minimal value, by choosing the sign of delta x, you can come to a contradiction. So the only thing is, the only possibility is that this partial derivative is zero. So this is just a reminder of some rather trivial part of calculus. But now we shall generalize it in order to minimize or extremize the action. We need to use this to generalize this setup a little bit. In what sense? Try to think how this problem, which you know and which I probably I should have spent these few minutes because it's all well known to you. But how can I relate this problem to the problem of minimization of this action? What should I do? How they are related in the first place? Yes?
So in order to minimize s, you need to use functional derivatives.
What is functional derivatives?
So, yeah, so it's more complicated than derivatives of the scalar, or with respect to a scalar. But so in the same way as you have a small variation from some scalar value of x1 star, you have some small variation from x of t.
Yeah, the only thing which I don't quite agree with is that it's more complicated than ordinary derivative. It's not. It's a very easy thing. Now, what I wanted to stress is that here we have a function, but it's even more than that. These two problems are directly, not symbolically, but directly related to each other. Let me explain this. The object we introduce here, this object is function, and it simply tells you, it tells you then you have n variable fixed. It is a prescription to get a certain number we call f. So we map the n points onto a real number f, complex number f. So that's what we call the function. You are given the argument, and you have a program or prescription or inspiration to get this, all this might be the same thing, or to get this number f. All right. Now, here we have what is called a functional, and it is denoted usually in this way. The functional is the following thing. You are given a function. Here you associated the real number with a set of n variables. Here you associate it with the function x of t. So given a function of x, somebody tells you what x of t is, you plug it in, integrate, and get the number. Okay? Now, in which, what would be the approximation in which this problem reduces to calculation of this function? I claim that it's very obvious that this is a certain limiting procedure, and you can always reduce it to calculating the function of n variable. So I'm trying to establish the connection, the genetic relation between the function of n variable and the functional.
Taylor expansion?
No, I don't want to go into Taylor expansion. What I want to do, we will go Taylor expansion to calculate, but at the moment I want to be very general. Imagine that the time, here we have x of t, the trajectory. And we have a particular trajectory x of t. And as I said, we can integrate and get the function. Now, how can I get, instead of functional, how can I get the function of many variables? Imagine that I discretize time. We don't know whether time is continuous or discrete, or most likely it is neither. But here we discretize time for purely technical or calculational reasons. Suppose we, instead of this interval, we split it into many points, and we have t1, tn, or they can be the same. You can, in principle, choose tn to be n epsilon. Not necessarily so, but so suppose I work with discrete time. What happens to my functional?
It becomes the same as the f over there. So
Exactly.
and
Yep. Yep, exactly. We simply say the trajectory is here, and this is, say, x1, this is x2, this is xn, and instead of this expression, after time discretization, we will get the function of n variable, and in the limit, so when the number of variables go to infinity, then you get continuous limit. And so differentiation of these functions, differentiations is easy to, we will define functional derivative in a moment. You can ask whether it makes sense, since when we have n variables, we know how to differentiate it, we get how to calculate partial derivatives. We also know how to integrate it. There is also the notion of functional integrals, not only functional derivatives, but this notion is used, well, it's most useful in quantum mechanics, but it's also useful in the theory of turbulence and so on. So when you have functional, you can always visualize it as a limit of the function with very many variables. To be more concrete, let's take this standard expression and discretize it. Maybe you can simply dictate to me what will be the function. First, what will replace the integral? Let's do it term by term. In the discrete I want the discrete approximation. So what will be standing instead of the integral?
Summation.
Yes. So we will have sum over t. T will be now or sum over n. Now we have to, and we multiply it by the interval, which is epsilon. Now, what will be, what will stand instead of the mass? It will remain the mass. Okay, 1/2 in our approximation will remain 1/2. So, but what about the x dot square? Yeah.
X of t n squared minus x of t.
Yeah. Yes, that's correct. So the derivative will be xn plus 1 minus xn square divided by epsilon square and minus v of xn. And as you will see in, I'm sure you're all aware how to derive the Newton from here. I will do it. I will remind you in a second how it goes. In the home exercise, you will derive the Newton equation for discrete times. But what I basically want to stress is that it's practically the same notion as if you know how to take partial derivatives, you know how to, it basically the same rules apply to functional derivatives. And I will define it in a moment. So you see, that's just to explain that it's just an ordinary function. Don't be scared by anything, but in particular by functional derivatives. What is more scary, I must say, is functional integrals. I spent many sleepless nights trying to work with them. But functional derivatives are very easy. Okay, so let's remembering this. Let me remind you the standard derivation just to set up notation. We do the we replace x of t we replace it by x of t plus delta x of t. Precisely as we did here. And we get s, the new s tilde, will be integral over dt, m divided by 2, x dot plus delta x dot square minus v prime, gradient of v, delta x. Actually, I wrote vectors here, but it's totally irrelevant for me at this point. You can look at one-dimensional particle just as well. So it's delta x minus phi, of course. And that's precisely the same which you would do here if you are asked to minimize. You can always translate from here to here. Now, the change of action is integral over dt m x dot delta x dot minus gradient of b delta x. And now one useful trick here, which is where we shall write x dot delta x dot as d dt of x dot delta x minus delta x. And so finally we get the following expression. By the way, it will not be probably asked in the home exercise, but I recommend you to carefully check this, what this procedure means in the discrete case. What is its integration by parts? But integration by parts has its discrete analog. So check it out when you do the exercise.
How do we define the notion that delta x is small? Are we saying that it's small at every point?
Yeah, we're saying we're acting formally like here. Namely, we're saying that we pick up only the terms linear in order to define derivatives. We pick up the terms linear in delta x and forget about everything else. Physically, it's of course related to the smallness of delta x. But formally, you can always, maybe the notation, another possible notation, you write down delta xi, you call it epsilon, some parameter epsilon, multiplied by some function yi of t, yi, and then you are simply saying, I am interested in terms containing linear epsilon, and only in them. And that's by definition. I'm going to say more or less this thing when I finish this calculation. Formal definition of derivative is just a coefficient in front of linear terms. If the point is non-singular, that gives you a unique finite answer. Singularity is another matter, but all right. So to finish with it, we have delta s tilde minus s, I will call delta s, and its integral dt minus mx double dot minus gradient of v delta x plus mx dot delta x at t2 minus x dot at t1 delta x at t1. Now I will, and now we will say that we look at the trajectories with fixed ends. So we compare the action on various trajectories, but which begin and end at the same point. Therefore, delta x at t2 and delta x at t1 are 0. And we derive the Newton equation as a condition of that delta s is 0. Now I shall explain it. That's the calculation. But now let's start thinking about the definitions, techniques, and so on. So in this case, it was all very elementary. But I still, actually, while I defined partial derivative, I still haven't defined what I mean by functional derivative, except by saying that it is a limit of partial derivatives. And that's very important and useful to remember, that it's a limit of partial derivative. But what is it more formally? So the functional is just the way you associate number with a function. In this case, it had this structure, but you can consider many other functionals. For example, let's consider the functional when s is x is equal to x at some moment t0. For instance, it's a functional because when you are given a function x of t, you know the value x at t0, and that's a functional. Or you can get a derivative of this function. How we calculate? On the other hand, more generally, we have the what is called the Lagrange function, which you, again, I assume you know this elementary analytic mechanics. You have this thing. You can imagine many other functionals, of course. How we calculate derivatives, functional derivatives of this function? You define derivative by saying that variation of this function is, namely, you, precisely as you do with partials, it's by definition the coefficient in front of the first variation. That's this thing is by definition called functional derivatives. And if it is 0, it means you have an extremum. The analog of this thing for partial derivatives is that the variation, if we call function f, df dxk delta xk, and that's it. And what we calculated here was the functional derivative of the original function. And now I'm asking you a simple question, but simple but important to actually get the feeling of these guys. I want to calculate delta s delta x of t for this thing. What is it? I want to calculate the functional derivative of this functional. Yes?
It's 0 everywhere except at t naught.
Yeah, pretty good, but a little more. I need a little more.
And it's 1.
Let me do it, and then I will supply you with a huge amount of possible functionals to be each of which is willing to be differentiated. First of all, let's what you said will be literally correct for the discrete case. If you have, say, n, and you are saying my function is just xn, then the partial, what is the partial of this thing, of this function? N is, say, 5 or some particular number. And I differentiate it with respect to xk, k arbitrary number. What is this?
Kronecker delta function.
It's Kronecker delta function. It's, as you said, it's 0 everywhere except, okay. Now I want to, the trick I want to use here, it will be convenient for me to write it down as an integral over dt, delta of t minus t0, x of t. That's the way to write down this functional. And now you probably can tell me what is the functional derivative. Of this guy. Using this expression. Yes, it's simply delta of t minus t0. And I hope you see the precise analogy here and here. Kronecker delta in continuum limit becomes the Dirac delta function. So we can actually look at something slightly more complicated. How am I doing with time? Let's see if I have something. For example, let's take S to be what will be the answer of our or I will do it. I will make it even nastier. How would you approach this? Well, you will begin. You have to begin with this, and then probably we'll leave it for the exercise. My only goal, there's nothing especially interesting in this about this functional, is just to show you how easy it is to differentiate. There are other example of functionals. For example, you can write down dt du x of t minus x of u square. You can try to differentiate this functional also. And again, once again, it's there's in all examples I know this discrete approximation gives you what you need. It is perfectly the same thing. Okay, so that's a little bit some beginning of variational calculus. As I said, I strongly recommend the book by the great mathematician Gelfand, called Gelfand and Fermat's Calculus of Variation. We will not need it for this course, but it's just I'm sure it will be useful for you to read. Okay. But you can say, so what? So I presented it in this strange way, and we indeed minimize it. The first thing which follows is that the equation of motion we observe in nature are of very special kind. You may ask the following question. Suppose I have some equations of motion, some dynamical system with some equations of motion. Is it always derivable from the variation of some functional? Can you always find the action variation of which will give you this equation? In this case, it will be pretty empty statement. If every thinkable equation satisfies allows this presentation, that's not terribly interesting. However, it is not, and to understand, we will do it in more details next time. But I will give you the discrete version of this statement. We assume we have n variables, and we have the function of n variables. This is our analog of the action. The equations of motion are just that. The general equation of motion, and what would be the general analog of some equations of motion? Not necessarily, not the Newton equation, but some other equation. This is for all of k is 1 to n. And so you can write down this function, and when it is 0, it is 0. Well, as we will discuss next time, the general equation of motion corresponds to the condition that fk is 0 for arbitrary fk. But fk is not arbitrary here. It's a derivative of this thing. Not any function is the derivative of this thing. It will become clear next time. But what I want to stress now is that it's a huge amount of information. The statement that the system is derivable from the variational principle by itself contains a very powerful information. It's highly non-trivial fact about nature. Well, we will see next time how it works in various practical problems. Let's stop here.